So now we proceed to the second part of chapter number 3. Okay, we have the following topics: integer representation. So we start with representation of integers. So we can use any integer greater than 1. For example, 2, 3, 4, and so on. Okay, all these numbers as the base. Okay, as the base when expressing in integers. Okay, any number or any integer, any integer greater than 1 as the base when expressing integers. We consider the following theorem. So let's say we have a positive integer b and the integer b is greater than 1. Then, if the integer n, which is a positive integer n, can be expressed uniquely, okay, can be expressed uniquely in the following form. Okay, in the following form, n equal to a sub k times b to the power of k. Okay, a sub k times b to the power of k plus a k minus 1 times b to the power of k minus 1. Okay, and we continue the operation. Okay, up to a1 times b to the power of 1, but no need to write the power for b. Okay, so a1b plus a naught times b to the power of 0. Again, because b to the power of 0 equal to 1, so we can omit this part, so it remains equal to a naught. Okay, so the integer, positive integer n, can be expressed uniquely in the following form. So where k is a non-integer value, k is a non-negative integer value. Non-negative, that means it could be 0, 1, 2, 3, and so on, because all these numbers are non-negative number. Okay, the value for the k can be any non-negative integer. So a sub I for I equal to 0, 1 to up to k. Okay, this value is 0, 1 up to k. Okay, the value for the I equal to 0 up to k. So ai are non-negative integer. Non-negative integer less than b. Okay, less than b. And ak, we need to make sure that ak not equal to 0 to make sure that the leading term is equal to number to the power of b. It's a quotient for the b to the power of k. That means we want to make sure this term appears. Okay, appears, because if ak equal to 0, that means bk, ak times bk automatically equal to 0. Okay, so in order to avoid that, we want to make sure bk exists in this addition, so we need to make sure that ak not equal to 0. Otherwise, ak bk also equal to 0. Okay, conversion to decimal expansion. Okay, let's see how to do the conversion. What is the decimal expansion of the integer that has this number to the base 2 as its binary expansion? Okay, that means we want to convert from the binary expansion becomes decimal expansion. So binary means it is base 2. Okay, binary means it's base 2. So that means the digit in this expansion must contains 0 and 1. Okay, this is binary digit. Okay, it could be 0 and 1. There is no 3, 4, and so on. There is no 2. Only 0 and 1 allowed to be the element for this expansion. So how about decimal? Decimal means to the base 10. Okay, so how many digits? We have 10 digits, start from 0, 1, 2, 3, up to 9. Okay, so decimal value means the combination of the following numbers. Okay, 0 up to 9. Okay, so in the binary expansion, the given binary expansion, we have 9 elements of 0 and 1s. There is 9 elements which are the combination between 0 and 1. Okay, hence our value of k equal to 9 minus 1, which is equal to 8. Okay, so why the value for the k equal to 9 minus 1? Okay, we're back to the previous definition. Okay, let's see carefully here. Okay, we have how many elements here? Okay, we have ak minus 1 up to a1. Okay, up to a1 there are k elements. Okay, 1, 2, 3 up to k. That means there are k elements. But then we have another element which is a naught. So that means the number of elements equal to k plus 1. Okay. There's no space here. We write it here. Number of elements, okay, equal to k plus 1. Okay. So how to know what the value for the k? So the value for the k is equal to the number of element minus 1. So it is the value for the k. Okay, so that is why the value for the k here is the total number of element, which is 9. 1, 2, 3, 4, 5, 6, 7, 8, and 9. So 9 minus 1. So the value for the k equal to 8. Okay, so the first step is to identify what is the value for the k. So k is equal to the total number of element or total number of digit. We minus with 1, so we obtain the value for the k. So this is the binary expansion to the base 2. So it can be represented like this: a8 b8 plus a7 b7 plus a6 b6 up to a1 b1 plus a0 b to the power of 0. Because b to the power of 0 equal to 1, so we omit that 1, so it becomes a0 as the final element, as the last element. Okay, next, okay, so we can write all these terms in the following table. So we especially for the a terms, so we have a8 a7 up to a0, and then we arrange the given expansion in the following table. Okay, we have 1 0 1 0 1 1 1 1 and 1. Okay, so from this table, the next step, okay, so we know, so we replace the value for the a. Okay, we have a8 equal to 1, we have a7 equal to 0, we have a6 equal to 1, we have a5 equal to 0, we have a4 equal to 1, we have a3 equal to 1, a2 equal to 1, a1 equal to 1, and a0 equal to 1 based on the previous table. Okay, so we put all these values to replace the value for the a's. Okay, based on the following table. Okay, so from this equation, we can omit all value with the coefficient 0. Because any number we multiply with 0, it is always equal to 0. So we can omit these two terms. Okay, we can omit these two terms. So we have the following equation. When we convert all the 2 to the power of 8 to the power of 6 to the power of 4 to the power of 3 to the power of 2 and to the power of 1, okay, to the actual values respectively. So we have 2 to the power of 8 equal to 256, 2 to the power of 6 equal to 64, 2 to the power of 4 equal to 16, 2 cube equal to 8, 2 square equal to 4, 2 1 equal to 2. Okay, so from this value, from this equation, so we can perform the multiplication. Okay, because the multiplication with 1, so we write all the original value. Okay, and then because we have all these digits, all these numbers can be simply added, so we have the sum is equal to 351. So this is the decimal expansion from the given binary expansion. Okay, so that's the conversion from binary expansion to decimal expansion. Okay, the first step is to identify what is the value for the k. K equal to the total number of digit or total number of element minus 1, and then we write this equation. Okay, and then we build this table. Okay, we pay one by one, start from A8 up to A0 based on the given expansion, and we replace the value for the AIs into the equation, and then we compute the value. Okay, so we omit all the value with coefficient 0 because the outcome is equal to 0. So finally we do the multiplication and addition until we obtain the single value. So this is the decimal expansion. Decimal means this number is combination of the digit between 0 up to 9. So in this number we have a combination of 3, 5 and 1. Among the most important bases in computer science are base 2, base 8, base 10 and base 16. Although we can make all integer value greater than 1 as the base, but normally in computer science we consider only the following numbers as the bases. Okay, well, we have the base 2, base 8, base 10 and base 16. For the base 2, it is called as binary expansion, so it contains a combination of two digits, okay, between 0 and 1. For the base 8, we call as octal expansion. So it is combination of 8 digits start from 0 up to 7. Okay, 8 digits, this one 2 digits, this one 8 digits. Okay, start from 0 up to 7. Okay, that means in base 8 representation there is no digit 8, 9. Okay, there is no digit 8 and 9, only 0 up to 7. Okay, for the base 10, okay, that we normally do, then we normally use in our daily lives. Okay, so we have base 10, what we call as decimal expansion. Okay, it contains a combination of 10 digits start from 0 up to 9. Okay, 10 digits start from 0 up to 9, combination of these numbers. So for the base 16, it is a mixture between numbers and characters. Okay, an alphabet. So we have 0 up to 9, and then we for the remaining 6 elements, so we have characters, okay, letters. So I have A, B, C, D, E and F to complete 16 elements. Okay, 0 up to 9, and then combined with letters, so we have A, B, C, D and F. So the 16 elements for the hexadecimal expansion. Okay, so for hexadecimal expansion, the letters A through F represent the digit corresponding to the numbers 10 up to 15. Okay, so let's see how to do conversion. Okay, when the given expansion is octal and we want to convert from octal to decimal. In the previous example, we convert from binary to decimal. In this example, we convert from octal to decimal. From base 8, we convert becomes base 10. Okay, so let's see how to solve this problem. So as you can see here, because this one is octal representation, so there is no digit 9 and 8, only 0 up to 7. Okay, so this is the way how to do the conversion. In the given octal expansion, we have 4 elements, 7, 0, 1 and 6. That means we have 4 elements. So how to know the value of k? K equal to the total number of element 4 minus 1. Okay, so the value for the k equal to 3. So we write the given expansion in the following equation form. So we have a3b cubed, because the value for the k equal to 3. So the leading term, the highest power for the power for the leading term equal to b to the power of k, which is k equal to 3. So we have a3b3 plus a2b2 plus a1b1 plus a0b0. Again, because b0 equal to 1, we can omit, so it remains as equal to a and not. Okay, and then again we build this table. Okay, and we pair between a3, a2, a1 and a0 with the corresponding elements. Okay, so A3 we pair with 7, A2 we pair with 0, A1 we pair with 1, and A0 we pair with 6. Okay, and after that we substitute all the value for the a's inside this equation. Okay, so we have, okay, 7 times b cubed, 0 times b squared, 1 times b plus 6. So this one can be omitted. So for octal, the value for the b equal to 8. Okay, for the binary, the value for the b equal to 2, right? Okay, in binary, we substitute the value for the b equal to 2. Okay, equal to 2. So for octal, we substitute the value for the b equal to 8. Okay, so we substitute this one as 8, this one as 8, so we have this equation. Okay, so I think this equation can be solved easily. You can take your calculator and compute all the values. So after we perform the multiplication and addition, so we come out this decimal value as the decimal expansion of the given octal. Okay, the next example is to convert from the hexadecimal form, okay, becomes the decimal expansion number. So how to do that? First of all, we count the number of elements inside the given expansion. So we have 5 elements, 2, A, E, 0, and B. So 5 elements, so the value for the K equal to total number of element 5, and then minus 1. So the value for the K equal to 4. And then we write the equation. Okay, so the given hexadecimal expansion equal to this equation. Okay, and because K equal to 4, so the highest power for the B equal to 4. Okay, and then followed by A3B cubed plus A2B squared plus A1B plus A0. And then we build this table. Okay, we pair one by one, A4 with 2, A3 with A, A2 with E, A1 with 0, and A0, A0 by with B. Okay, and then we substitute the value for the A's inside the equation. So we have 2A, E, 0, and B. Okay, and in the hexadecimal expansion, we need to substitute the value for the b equal to 16. Okay, the value for the b equal to 16. So note that, okay, remember that, okay, in hexadecimal, the letter A up to F actually represent the digit corresponding to 10 up to 15. That means A equal to 10, B equal to 11, C equal to 12, D equal to 13, E equal to 14, and F equal to 15. Okay? So, equal to 15. So, from the equation, so we can substitute the value for the A equal to 10, and the value for the E equal to 15, and the value for the B equal to 11. Okay, so we can compute the value now. Okay, because all numbers are in all elements are in numerical form, so we can compute the value. Okay, so this one can be omitted because 0 times anything, it is equal to 0. So we compute. So after do the multiplication and also addition operations, so finally we come out with this expansion, okay, which is the decimal expansion of the given hexadecimal expansion. Okay, so from the previous few examples, we convert from binary to decimal, from octal to decimal, and also from hexadecimal to decimal. So how to do the reverse process? That means from decimal we convert, it becomes binary. Okay, from decimal becomes octal, or from decimal becomes hexadecimal. Okay, so we consider the following example. We start with the first case, which to convert uh, to convert the given decimal to octal expansion. Okay, from base 10 we convert to base 8. Okay, so let's see how to do the conversion. So first of all, we need to divide the given number, the given decimal number by 8. Why 8? Because we want to convert to octal expansion. So we divide by 8. So the divisor equal to 8. To get the first quotient Q1 and the remainder R1. Okay. So after we divide 1, 2, 3, 4, 5 by 8, so we obtain the first quotient equal to 1543 and the remainder equal to 1. Okay, so we have Q1 equal to 1543 and R1 equal to 1. But then we have to continue the same process. Okay, we take Q1 as the new dividend and we divide again by 8. Okay, and to obtain a new quotient and a new remainder. So we do the same process until you obtain the quotient equal to 0, then we stop. Okay, so from this step, we have a Q1 as the new dividend. Okay, we divide by 8. 1543 divided by 8, so we obtain the next dividend is equal to 192, and the next remainder equal to 7. Because the quotient equal to 192 not equal to 0, so we need to proceed. We take this this quotient becomes a new dividend. Again, we divide by the same divisor, which is 8, to obtain a new quotient 24, and the remainder equal to 0. Because the quotient 24 not equal to 0, that means we need to proceed. We divide 24 by 8 to obtain a new quotient 3. Okay, so again, because the quotient 3 not equal to 0, so we need to proceed with the next step. We divide the new quotient 3 by 8. Okay, so we divide 3 by 8, the quotient equal to 0 because 3 is smaller than 8. So the quotient equal to 0 and the remainder equal to 3. Then we stop. Okay, so we stop. So the successive remainder that we found as follows. Okay, so that means our interest is at on the reminders. Okay, so this one is the value for the R1. This one R2, R3, R4, and this one is the final one, R5. Okay, therefore the octal expansion of this decimal number is actually the value for the remainder. Okay, we arrange the remainder, start from the last one, which is R5, followed by R4, R3, R2, and R1. We put in parentheses and we put subscript n to indicate this is an octal expansion of the given decimal expansion. Okay, so it is equal to 30071. Okay, clearly there is no digit 8 and 9, only digits from 0 up to 7. So this is an octal representation or octal expansion of the given decimal 1, 2, 3, 4, 5. Okay, so find the hexadecimal expansion of the given decimal value. So divide. Okay, we do the same process, just the previous example, but then we change the divisor. In the previous example, we have 8 as the reminder as the divisor, but for the hexadecimal expansion, okay, so our divisor is equal to 16. Okay, so we divide the given decimal number 177130 by 16 to get the first quotient and the first remainder. Okay, so our first quotient is equal to 1070. Okay, this is the first quotient. So the first remainder equal to 10, but our interest now is on the quotient because we want to take this quotient as the new dividend in the next step. So we divide the new dividend by 16. We obtain a new quotient which is equal to 691. Okay, 691 is a new quotient plus the remainder equal to 14. Because the quotient not equal to 0, we need to proceed. We take 691 becomes a new dividend. We divide by 16, we obtain a new quotient, which is equal to 43. Okay, because the value for the quotient not equal to 0 yet, so we need to proceed. So the next step, we take 43 as the new dividend. We divide by 16, the outcome is equal to 2 as the quotient and 11 as the remainder. Because the quotient now is not equal to 0, so that means we need to proceed again. We take 2 as the new dividend because 2 is smaller than 16, so the quotient now equal to 0 and the remainder equal to 2. Okay, so because the quotient now equal to 0, then we stop. Okay, so after we stop, so we take note about the remainder for each step. Okay, so we have R1 equal to 10, R2 equal to 14, R3 equal to 3, R4 equal to 11, and R5 equal to 2. Okay, and then we notice that we have some numbers that is greater than 9. So we have 10, 14, and 11. So remember, 10 up to 15 are represented in characters form or in letters form. So 10 equal to A, 11 equal to B, 12 equal to C, up to 15 equal to F. So we have 10 equal to A, okay, 11 equal to B, and also 14 equal to E. So in the hexadecimal representation, we arrange all the reminders from R5 followed by R4, R3, R2, and R1. So we have 2, okay, B, 3, E, A, and then put in parentheses, put subscript 16 to indicate this is the hexadecimal representation of the given decimal expansion. Okay, so remember, for all values, for all the remainder with a value greater than 9, that means 10 up to 15, we need to convert that numbers into characters form. Okay, so we have A equal to 10, B equal to 11, up to F equal to 15. Okay, in this case, we need to substitute 10, 14, and 11 with A, B, and E respectively, and we put as the hexadecimal representation of the given decimal expansion. Okay, so finish with that. So we have another algorithm to consider in this chapter, which is the fast powering algorithm. Okay, so it is discussed about under the topic of modular exponentiation. Okay, previously we learned about the modular addition and also modular multiplication. Okay, so in this topic we are discussing about modular exponentiation, exponent operation in the set of integer modulo m. Okay, so fast powering algorithm. Fast powering algorithm can be deployed by to compute the value for the b, n mod m efficiently, where b, m, and n are large integers. Okay, so let's say I give you a task to compute the following number. Compute 3 to the power of 218 mod 1000. Okay, can you use your calculator to compute this value? Can you directly compute 3 to the power of 218 using your calculator? So it's impossible unless you're using programming, yes. But using your calculator, it's impossible, okay? Beyond the capacity of your calculator. So how to do this exponentiation? So this is what we call as exponentiation because we have modular operation. So this operation is called as modular exponentiation. Okay, 3 to the power of 218 is exponentiation, but once we have a modular operation, okay, mod 1000, so we say that this is a modular exponentiation. Okay, so how to compute 3 to the power of 218 mod 1000? So this task can be done easily by using fast powering algorithm. Okay, so the first step in the fast powering algorithm is to convert the decimal value for the decimal form of the exponent value, which is 218, to binary expansion. That means from base 10, we convert becomes base 2. Okay, so how to do that? So just like the previous examples, for octal, the divisor equal to 8. For hexadecimal, the divisor is 2. So for decimal to binary, the divisor equal to 2. Okay, so we divide the value 218 by 2. We obtain the first quotient equal to 109 and the first remainder equal to 0. Because the quotient not equal to 0, we proceed. We take this quotient as the new dividend. Again, we divide with the same divisor, which is 2. So we divide by 2. The new quotient is 54. Okay, because the quotient not equal to 0, we proceed. We take 54 as the new dividend. Divide by 2. We get the new quotient. Because the quotient not equal to 0, we proceed. Okay, we take 27 as the new dividend. We divide by 2. We obtain new quotient, and then we divide again the new quotient by 2. We obtain the new quotient equal to 6. We divide 6 by 2. We obtain 3 as the new quotient. We divide 3 by 2. We obtain 1 as the new quotient. And we divide 1 by 2 because 1 is less than 2. So the quotient equal to 0 and the remainder equal to 1. Because the quotient now equal to 0, then we stop. Okay, so once we stop, so our interest is on the remainder. So we denote all the reminders from the first one as R1, R2 up to R8. Okay, so make sure you follow the correct arrangement. Okay, from R1 up to R8. Then we rewrite the decimal expansion in the following form. So we have R8 up to R1. So we just simply substitute the value as follows. R8 equal to 1, R7 equal to 1, up to R1 equal to 0. So we have, this is the decimal expansion of the exponent to 218. Okay, so finish with the first step. So what is the second step? Okay, the second step, okay, is to identify the value for the k. Okay, so the value for the k is based on the binary expansion. Okay, not the decimal, but the binary expansion. So we count how many elements inside the binary expansion. So there are 1, 2, 3, 4, 5, 6, 7, and 8 elements. So the value for the k equal to the total number of elements, which is 8 minus 1, and the value for the k equal to 7. Okay, the value for the k equal to the total number of elements, which is 8 minus 1. So it is equal to 7. Okay, the next step is to rewrite the binary expansion in this equation. Okay, so we have a7 times b to the power of 7 because our k equal to 7. So we write up to a naught. Okay, and then we build this table. Okay, this time we pair a7 up to a naught with the binary expansion. Okay, with the corresponding binary expansion. So we have a7 equal to 1, a6 equal to 1, a5 equal to 0, up to a0 equal to 0. And then we substitute the value for the a's, okay, based on the value for the a's inside this table. So we have a7 equal to 1, a6 equal to 1, a5 equal to 0, a4 equal to 1, a3 equal to 1, a2 equal to 0, a1 equal to 1, and a0 equal to 0. Okay, so for binary expansion, the value for the b equal to 2. The base is 2, right? So the value for the b equal to 2. So we substitute all the value for the b equal to 2. So we obtain this equation after we omit the numbers with the 0 as the coefficient. Okay, so the remaining values are 2 to the power of 7 plus 2 to the power of 6, 2 to the power of 4, 2 to the power of 3 plus 2 to the power of 1. Okay, do not compute the value. Okay, not yet. Our interest is not to the value, but our interest is at the exponent value. Our interest is on 7, 6, 4, 3, and 1. Okay, so let's see what is happen in next step. In the next step, okay, we arrange the value for the I equal to 0 up to I equal to 7. Okay, from I equal to 0 up to I equal to 7. So we stop at 7 because our K equal to 7. So we stop at 7. So for the I equal to 0, so remember our initial problem is 3 to the power of 218 mod 1000, right? Okay, so we take 3 as the base now. Okay, so 3 to the power of 1, the value equal to 3. For the I equal to 1, we have 3 square. Okay, we take this 3 to this side. So we have 3 square equal to 9. Okay, the next step, when I equal to 2, we take 9 to this side. So it becomes 9 square. 9 square equal to 81. Okay, in the I equal to 3, we take 81 to this step. So it becomes 81 square. So now the value for the 81 square exceeds 1000. Okay, the value is 6,561, which is greater than 1000. So because the value is greater than 1000, that means we need to reduce it modulo 1000. Okay, so we need to divide it by 1000 and we find the remainder. So the remainder is equal to 561. So we take 561 instead of 56661 to the next step. Okay, not this one, but this value after we do the modulo reduction. So we take 561 to the next step. So we compute 561 square. Again, the value exceeds 1000. So because of that, we need to reduce mod 1000. Okay, if the value is smaller than 1000, then let it be. We just take the original value to the next step. But if the value exceeds 1000, we need to do the modulo reduction first before we take that value to the next step. So after we do the modulo reduction, the outcome is equal to 7 to 1. Okay, this is the remainder when we divide this number by 1000. So this is the remainder. So we take this remainder to the next step for I equal to 5. In I equal to 5, so 7 to 1 square, again the value exceeds 1000. So we do the modulo reduction. This is the outcome. We take to the next step. Again, we compute 8 for 1 square. The value also greater than 1000. So we compute the modulo reduction. We obtain 281. We take to the next step. In the final step is I equal to 7. So we have 281 square. The value exceeds 1000. We reduce mod 1000. The outcome is 691. Okay. So we stop at I equal to 7 because our value K equal to 7. So next, okay, in the next step and the previous step, we consider the exponent value of 2, right? 76431. Okay, so in this step, we also consider the same values for I. Okay, so we consider the value for the I, 7, I6, 4, 3, and 1. Okay, based on the exponent value of 2 in the previous slide. Okay, same values, 7, 6, 4, 3, and 1. And our interest is the corresponding value for all these numbers. Okay, for I equal to 1, the value equal to 9. For I equal to 3, the value is 561. I equal to 4, the value equal to 721. Okay, for I equal to 6, the value is 281. I equal to 7, the value equal to 961. Okay, so by taking all these 5 numbers, okay, so the value for this modular exponentiation is equal to 9, 561, 721, 281, and 961. We do the multiplication operations on these smaller numbers. Okay, so you have option. If you cannot compute directly these 5 numbers, you can do it twice. Okay, by separate these 3 numbers first. Okay, we multiply these 3 numbers and then we reduce mod 1000. The outcome is this smaller number, and then the remaining numbers 281 multiply this one, we obtain this number, which is smaller number. Okay, So because these two numbers exceeds 1000, you can reduce these two numbers mod 1000. So it becomes 329 and also 49. It becomes these two numbers become smaller than the original value. So it's very easy for you to compute 329 with your calculator. Multiply with 41 using your calculator, you obtain the value equal to 13489. So because this number also exceeds 1000, greater than 1000, so you need to do the modular reduction operation. Okay, so divide by 1000 and find the remainder. So the remainder equal to 489. Okay, so originally 3 to the power of 218 mod 1000, okay, is impossible to compute using your calculator. Okay, but by using the fast powering algorithm, now it becomes possible. Okay, so the answer is equal to 589. Okay, so make sure the answer is smaller than 1000. Okay, because this is the modular reduction operation is mod 1000. The answer must belongs to the set of integer modulo 1000. So 489 is smaller than 1000. So it belongs to the set of integer modulo 1000. Okay, so in this topic we discuss about prime numbers and also greatest common divisor. So what is the definition for the prime number? So prime number is an integer greater than 1. So it must be greater than 1. That means the smallest one is 2. Okay, the smallest possible prime number is 2. Okay, what is the next condition? The next condition, the only positive divisors are itself and 1. Okay, that means there are two only divisors for the prime numbers. The first one is itself and the second one is the integer 1. So let's check for the integer 2. Yes, integer 2 can be divided by itself which is 2. So 2 by 2 equal to 1. 1 is an integer. And also can be divided by 1 only. Okay, so 2 only has only two possible divisors, which are itself and 1. Okay, only two possible positive divisors, which are 2 and 1. So 2 satisfies the condition to be a prime number. So what is the next prime number? 3, because 3 can be only divided by only two integers, okay, which are 1 and 3. Okay, so 3 is a prime number. So how about 4? Okay, so 3 can be divided by 3 and itself. So how about 4? So 4 can be divided by 1, can be divided by 2, and can be divided by itself. So it doesn't satisfy the condition to be a prime numbers because it has 3 positive divisors. Okay, to be a prime numbers, there are only 2 positive divisors, which are itself and 1. But for 2, there are 3 divisors, 1, 2, and itself. So 2 is not a prime number. So for a not prime number, we call this kind of number as composite number. Okay, if it is not prime, so it is a composite. So composite number is an integer that is not prime. So 4 is a composite number. 4, 6, 8, 9, okay, 10, 12, and so on. So all these numbers are composite numbers. So logically, to determine whether an integer p is a prime or not, so we can check the potential divisors from the following list. We start from the number 2 up to p minus 1 and we check, okay, is there any other divisor? Okay, is there any other positive divisor other than 1 and itself for any prime number, for any number p? So if there is no other divisor other than 1 and itself, so that number is a prime number. Okay, so but to check one by one is quite cumbersome. Okay, especially when p is large numbers. So it's very totally inefficient if you want to try find the divisor for the p by dividing p with all numbers between 2 up to p minus 1. For example, let's say I give you p equal to 711. Okay, so to divide p with all numbers from 2 up to p minus 1 is quite, obviously it is difficult and totally inefficient. Okay, so, okay, if none of the integer divides p, then we can say that p is a prime number. If there is no number between 2 up to p minus 1 can divide p, okay, that means p is a prime. Okay, otherwise p is composite. Okay, that is when we think logically. But then mathematically, actually instead of dividing p with numbers from 2 up to p minus 1, we can shorten the steps by dividing p with numbers from 2 up to the floor of square root of p, which is much smaller than p minus 1. Okay, so the floor of square root p is smaller than p minus 1. So this list is shorter than the previous list. Okay, shorter than the previous list. But again, if p is a large numbers, so these steps also could be cumbersome. Okay, totally inefficient. Okay, so I give you example. Determine either the following integers is a prime or composite. 29. So how to determine whether 29 is a prime or not? So instead of dividing 29 with by 2 up to 28, we can shorten the list. So we can divide. Okay, first of all, we find the value for the floor of square root 29. The square root of 29 equal to 5.4. So the floor is equal to 5. Okay, so you can check the potential divisors from the list 2, 3, 4, and 5. If any number from this list can divide 29, so 29 is a composite number. Because in order to be prime number, the only divisor for 29 must be either 1 or itself. Okay, only the two numbers. Okay, either 1 and itself. But if there is other divisor from this list can divide 9, then so can divide 29, so 29 is a composite number. So we check one by one. We divide 29 by 2, we divide by 3, 4, and 5. So we notice that all these divisors fail to divide the 29 number. Fail to divide the 29. Okay, so 29 is concluded as a prime number because from this list, none of these numbers can divide 29. So the only divisors for 29s are 1 and 29. So 29 is a prime. So how about 27? So for 27, so we can compute the floor of square root 27. The value equal to 5. So we list down all the numbers 2, 3, 4, and 5. And we try to divide 27 by these numbers. So we notice that, okay, 27 is divisible by 3 because 27 divides by 3 equal to 9. So 9 is an integer. So because of that, we conclude that 27 is a composite number. Okay. So according to this theorem, so let's say we have positive integer n, where the integer n greater than 1. The integer n is composite if and only if n has a divisor d. Okay. A divisor d satisfying that the d is located between 2 and the square root of n. Okay, so the integer d greater than or equal to 2 and less than or equal to n. So if this divisor exists, so that means the number n is a composite number. Okay, so according to the fundamental theorem of arithmetic, so if we have positive integer a where the positive integer n where the integer n is greater than 2, okay, so this n can be factored, okay, can be factored as a product of prime numbers. Okay, product of prime numbers. So the first prime number denoted by P1, the second prime number equal to P2, up to the rth prime number equal to PR. And all these prime numbers has their own exponent value. Okay, so according to the fundamental theorem of arithmetic, so every positive integers greater than 2 has this kind of factorization. So any numbers n, positive number n that is greater than 2 can be factored to these prime factors. And all these prime numbers has their own exponent value. So other than rearranging this prime, so actually this factorization is considered unique for all numbers. Okay, for example, 10. Okay, 10 is greater than 2. So 10 can be factored to two prime factors, which are 2 and 5. Okay, so for 10, equal to P1 E1 plus, multiplication means, factors mean multiplication. P2 E2. Alright, so the first prime number is equal to 2 and the exponent value equal to 1. Okay, multiply the second prime number is 5. Again, the exponent equal to 1. So this is the prime factors of 10. For the one, for the first prime E1 multiply the second prime E2. So the first prime is 2, the exponent is 4. Multiply by the second prime is 3 and the exponent is 2. Okay? So 2 and 3 also a prime number. So all these numbers 1661, 164 and this number, all these numbers has their own prime factors. Okay, for 1661 the prime factors are 11 times 151. So 11 is a prime, 151 also is a prime. For 164, it can be factored as 2 squared times 41 to the power of 1. So 2 is a prime, 41 is a prime. So for 4880, it can be factored to 2, 4, 3, 2, 2 to the power 4 times 3 squared times 5 times 2 to 9. So 2 is a prime, 3 also prime, 5 is a prime, 2 to 9 also is a prime. Okay, so all numbers, basically all numbers, as long as that numbers is positive and greater than 2, so all these numbers has their own prime factors according to the fundamental theorem of arithmetic. So, okay. Next is about the greatest common divisor. Okay, so we consider the following definition. As I mentioned to you in the previous slides, to find the divisor is quite cumbersome, right? If we try to divide one by one, so when the value for the piece large, so it's very difficult and it's quite it's inefficient for you to find the divisor. Okay, so we have technique to find the divisor efficiently, and the technique is what we call as the Euclidean algorithm. So before we cover the Euclidean algorithm, we need to understand first about the greatest common divisor. So we define two positive numbers, a and b, two positive integers, where a and b not equal to 0. So the greatest common divisor of these two numbers, a and b, is the largest integer d that could divide both numbers a and b. That means d is the largest positive integer that divides a and also divides b. We are looking for the largest one. So that is we call it as greatest common divisor. Greatest means the largest one. The largest common divisor between a and b. Okay, so how to write the GCD. So to write the GCD, we need to use this notation. So we use the small letters GCD. We put the A and B inside the parentheses. So A and B, we put equal to D. Okay, so this is the complete notation for the GCD. Okay, you need to write the notation completely, because in exam I know, okay, some of you will try to use the simpler notation. How the simpler notation? Compute the GCD, so you just simply write because sometimes in exam some students just simply write the GCD as GCD equal to, for example, 8. This is incomplete notation because we don't know GCD of what. So that's why you need to write completely. Okay, the notation, the GCD of two numbers a and b equal to d, then you get the full marks for this question. Okay, so make sure you use your correct notation. as your final answer. Okay, so the divisor, let's say I give you two numbers, 748 and also 2024. And I'm looking for the greatest common divisor of these two numbers. So traditionally, okay, what we can do to solve this problem is by listing all the divisors of both numbers. So we put all the divisors for the 748 inside this set, okay. So all these numbers can divide 748 without any reminder, and we also list all the divisors for the 2024 inside this parenthesis, okay, inside this set. Then we are looking for the common values inside this set. Okay, we have 1, we have 4, we have 2 common value inside these two sets for n44. And among all these common divisors, the greatest one is 44. Okay, among all these common divisors, so we know that the largest one is 44. So that is why the greatest common divisor for these two numbers equal to 44. But, okay, to do the traditional way is totally inefficient because you need to list down all the possible, all the divisors and then find the largest one. So if the given numbers A and B are large, so totally the previous way are inefficient at all. Okay, so you need an algorithm to complete this task. So fortunately, we have an algorithm that makes this task easier to solve. So we have what we call as Euclidean algorithm. Okay, so let's say we have two positive integers A and B, where A is greater than B. Okay, so we put the larger number in front, we call it as A, and the smaller one we denote as B. Okay, so we have A greater than B, and we need to make sure that B not equal to 0 because the B becomes the divisor in this algorithm. So when divisor equal to 0, so the division becomes undefined. So we need to make sure B not equal to 0. So the Euclidean algorithm is used to compute the GCD of A and B. Okay, so let's see how to solve this problem. So the question asks you to compute the GCD of two numbers 2024 and 748. Okay, so because 2024 is greater than 748, so we let n equal to 2024 and we let d equal to 748 because we want the larger one as the dividend and the smaller one as the divisor. So we have the following equation: n over d equal to q plus r over d. When we rearrange, we obtain this equation. Okay, n, d, q, and r. We already have n and d. Okay, our n equal to 2024. We also have the d, but then we need to find two values, q and r. Okay, so we divide the dividend by the first divisor. We obtain the first quotient and the first remainder. Okay, because the remainder is not equal to 0, so this time we consider the remainder. In the previous examples, we consider the quotient. As long as the quotient not equal to 0, we proceed. But in the Euclidean algorithm, we consider the value for the remainder. As long as the remainder not equal to 0, so means we need to proceed until the remainder equal to 0, then we stop. Okay, so in the first step, we have 2 as the quotient and 7 to 8 as the remainder. So we take the dividend to the next step becomes a new, the divisor 7 for 8. We take this divisor as a new dividend, and the remainder as a new divisor. Okay, so the divisor in the first step becomes a new dividend, and the first remainder becomes a new divisor. So we divide, we obtain the quotient equal to 1 and the remainder equal to 2 to 0. Because the remainder not equal to 0, we need to proceed. We take the divisor 5 to 8 as the new dividend, and we take the remainder 2 to 0 as a new divisor. So we divide 5 to 8, divide by 2 to 0, the quotient equal to 2 and the remainder equal to 88. because the remainder still not equal to 0 yet, so we have to proceed. So we continue, we take the divisor as the new dividend and the remainder as the new divisor. Okay, so the quotient equal to 2, remainder equal to 44. Since the remainder not equal to 0, so we need to proceed. We take 88 as a new dividend and 44 as the new divisor. So this time, we obtain the quotient equal to 2 and the remainder equal to 0. So once the remainder equal to 0, then we stop. So we take the previous remainder, the remainder before 0, as the value for the GCD. Okay, so the GCD for the given numbers 2024 and 748 equal to 44. The value prior to the remainder equal to 0, which is 44. Okay, so the GCD of these two numbers equal to 44. Okay, so for this problem again, we are given two numbers 5 to 5 and 235. So the larger number will become the dividend and the smaller one becomes the divisor. So we compute the new quotient and new remainder. Okay, so we in the next step we take the divisor as a new dividend and the remainder as the new divisor. We obtain a new quotient and also a new remainder. Okay, because the remainder not equal to 0, we proceed. We take the divisor as a new dividend and the remainder as a new divider. Okay, the remainder as the new divider. So we obtain a new quotient and new remainder. Because the remainder not equal to 0, we proceed. We take the divisor as a new dividend and the remainder equal to as the new divisor. Okay, so we obtain the quotient equal to 1 and the remainder equal to 5. Because 5 not equal to 0, we need to proceed. In the next step, we take 10 as the new dividend and we take 5 as the new divisor. So when we divide, we obtain the quotient equal to 2 and now the remainder equal to 0. Because the remainder equal to 0, then we stop and we consider the previous remainder before 0 as the GCD of the given numbers. Okay? So that's the way how to compute the GCD by using the Euclidean algorithm. Okay, so that's all from this part. Thank you.